the value that we have in, all the high performance computers are, what we can really extract from the data we have is tremendous.
Welcome to Infrastructure Connections, the podcast where we explore what makes sustainable infrastructure work, brought to you by the Infrastructure Sustainability Council. I'm your host, Seth Scott, and today we'll be speaking about how AI and physics create high-resolution climate projections with our guests, Dr. Peter Gibson and Neelesh Rampal. Dr. Peter Gibson is a climate scientist at NIWA, the National Institute of Water and Atmospheric Research here in New Zealand. He focuses on regional and global climate modeling and the physical processes behind extreme weather and climate events. Neelesh Rampal is a data scientist also working at NIWA. He specializes in artificial intelligence. He also holds a master's in physics from the University of Auckland. Welcome to the show.
I'm Neelesh Rampal. I work as a climate data scientist at NIWA, so I do a bit of both, working on in the climate science space, but I also work a lot with using kind of novel artificial intelligence approaches to basically help our climate science. So that's my role. What about yourself, Peter?
Yes, I'm Dr. Peter Gibson. I'm a climate scientist here at NIWA. My main focus is on physical climate modeling, so using physics-based climate models to better understand and predict, future climate risks. And my research is often also focused on extreme weather events, which are obviously the most damaging to society. So trying to understand those and predict how they're changing with climate change. And stoked to be on the podcast today. Thanks.
Yeah, thanks for having us on here.
Thanks a lot. Yeah, I'm just curious, AI, physics, data, there's a lot you can do with that. You could have gone to Wall Street, I imagine. So what made you decide to go into climate change research?
You go first.
Sure. Yeah, I think for me, I think my first sort of exposure to climate science was through, I think it was around 13, 14, when I first saw Al Gore's Inconvenient Truth documentary. And for me, that was sort of I just wanted to learn a lot more about the science of climate change. So went on a pretty big deep dive in my own time. Obviously at high school back then, there weren't dedicated courses on climate or anything like that. So did a lot of my own research and really wanted to work in this field. But even also when I started at university, there also weren't dedicated courses then to climate science. So I sort of did my own a combination of maths, physics, environmental science. And that sort of came together in a way that when I started my postgrad, it was a nice foundation for that. But yeah, didn't set out to necessarily I want to be a climate scientist. But I think one thing I really enjoy about it is that, as you say, that combination of using physics, using numbers and statistics to work on a problem of global significance that can hopefully help climate resilience and by better predictions of climate change help save lives.
That's a long journey. I'm glad you made the right choice.
Yeah, for me it was sort of similar. I think I actually really wanted to. I think it started off being an astrophysicist, and then I think when I was in my early 20s, I'd often find myself while I was flying on a plane. I think I flew from Auckland to Bali, and for the 9 hours of my whole plane journey, I just stared at the clouds and sort of took notes, which is a very nerdy thing to do. And so that's when I changed from doing sort of an astrophysics-based approach, doing physics, to climate. I was like, I feel like I can relate a whole lot more to this problem, and just seeing how fascinating, how beautiful clouds are. It was truly incredible. So I really wanted to study, specifically, I wanted to go to Antarctica. And I found a project about Southern Ocean clouds. And I thought maybe if I could study Southern Ocean clouds, I would find my way to Antarctica. Unfortunately, you can study clouds by satellite. So I ended up becoming a disk-based person, studying satellite images of clouds. But it's been an absolute pleasure, like the value of satellite data, the value that we have in, all the high-performance computers are, that what we can really extract from the data we have is tremendous. And so for me, the amount of data we have, it's inevitable that we're going to use data science to do it. So the cool thing about my work is being able to sit at the, sort of the boundary between climate science and AI. We really need both. There's so much value in both. And, bringing the two disciplines together has been just absolutely exhilarating. So that's kind of what brought me to this area of work.
Well, I've always wanted to go to Antarctica too. I even applied as a chef, I think, but it's probably just as well. They would all got food poisoning. But yeah, keep the dream alive.
Yeah. I'm not too sure how useful I am there, but anyway.
So while you're working on climate change, I imagine you've come up against big problems, obviously. But what's one of the main problems you've been trying to solve but has always maybe proven elusive or extra difficult?
Yeah, I think one of the grand challenges of climate science is to make our climate projections more meaningful for people on the ground.
Yeah, and so the hard aspect of the problem, the reason why our area is hard, is we're trying to basically understand, for example, how is extreme rainfall changing here in Wellington, in Sydney, and Auckland, and this matters for obviously infrastructure. And many other, big, other projects that we need to do. So for us, it's all about how can we make these physics-based models help us understand how is rainfall, how is temperature going to change. And temperature might change differently in different locations. So if you're in Auckland, the mountains change differently to how the city changes. And we really need to capture that in our models. And that's something that we're doing in our modeling.
So back us up a little bit for people who don't know much about climate modeling. How does the global model start with? How's it developed, and how's it turned into these regional models on the grid level that you were talking about?
Yeah, so it can do a bit of a climate modeling 101 if you like. So global climate models, these are developed sort of around in the main modeling centers around the world, which, as you'd imagine, are the big, sort of usually government labs that have the resources to develop and run these models. And so every 5 years or so, the IPCC puts out, a new assessment report, and these climate models, are developed on those cycles as well in a process called CMIP, Coupled Model Intercomparison Project. And the results from that feed into these IPCC reports. And so these are, as I said, global models. Basically what it involves is taking this Earth sphere and atmosphere and dividing these into grid cells. And at each of these grid cells, we solve equations of motion in the atmosphere. So fluid dynamics equations, essentially. And other parts of the atmosphere and ocean and land are coupled and talk to each other in these climate models. And these are fairly big pieces of software. So a typical climate model might be, is typically over 1 million lines of code. So not something that one person, has built themselves. These are teams and really multi-generational pieces of software. So that's part of it. And then to run them, also requires, huge compute, not something you'd run on your laptop, for example. They run on big supercomputers. So one limit, so despite all that sophistication and effort, a limitation of global climate models is their spatial resolution. So each grid cell in the models, when we break up the sphere of the Earth, is typically about 100 kilometers in your standard climate model today. As you can imagine, over Australia or New Zealand, this isn't sufficient resolution really to answer local, or regional questions about climate change, such as, on this side of the mountains, how does climate compare to this side of the mountains? Because the mountains are influencing, these things quite a bit. So what we do here at NIWA in our regional modeling team, we run a regional model from the output of these global models. So the global modeling community makes all their output publicly available, which is an awesome resource. You're talking tons and tons of data, petabytes of data, if that makes any sense. So that's like a lot of data that you can download. And so we download we select some of the top performing global models for our region. There's sort of over 50 you can choose from. We choose the top performing ones, and then we downscale with a regional model. So the regional model is typically similar in formulation to the global models, but it's focused over a specific region.
So Neelesh, let's talk about AI. I'm assuming most people don't know much about AI. I'm talking about me here. Most people are familiar with ChatGPT, writing emails. But so obviously in simple terms, what kind of AI are you using? I imagine you're not using ChatGPT to come up with this information. How does that AI get built? How do you use it? What is it? Just in very, very simple words.
Yeah, so I mean, ChatGPT is what we call so it's basically language. So it's a natural language model, basically NLP. I sort of use convolutional neural networks. So neural networks or convolutional neural networks are modeled basically how our sort of brain makes decisions, neurons. And so basically they're a similar process to how our brain might make decisions. And so in the case, I give you an example, basically. For examples of these include like facial recognition. So you might have Face ID on your phone, and so your phone scans your face and learns that it's you, right? In the same way we have self-driving cars. We've got cameras in the front, and the car itself is trying to make a decision on, should I turn left, should I turn right? And that's the sort of AI we're using in our research, what we call sort of visual AI in our case. So it's really, I mean, you think about it, we as humans really easily can recognize faces and make decisions. We know that if there's a tree on the road, we turn, we stop and we move out away from the tree. But how do you tell an AI to make that same decision? It's actually a really much more challenging problem. And the way we do it is by giving AI data. The more data we give it, the more it has the ability to learn what is the tree and what is the road. And so it will start learning things as, what is the texture of the tree, and how does the texture of the tree differ from the texture of the road? And so you can kind of think of AI as learning that the tree has more contrast or more texture as opposed to what a road has. And that would hopefully inform its decision making on to stop the car. So in the same way we're detecting face, it will learn to recognize what's our specific nose pattern and so forth. So again, you could kind of think of the AI as learning things like contrast or edges of my face and learning how to make a decision based on that. So, yeah.
How does that play into the climate modeling then?
So basically the example would be, we're trying to basically predict rainfall or temperature. So Peter introduced the global climate models, which are a very low resolution. And what people want is ultimately to have high resolution climate projections, so we can resolve how extreme weather will change over cities like Wellington, Auckland, Sydney. And so this becomes a pretty similar problem. We're trying to predict rainfall and temperature based on what the weather or what the winds are doing, basically. And so the model is now trying to learn, given what the winds are doing, given what the pressure is doing, will it rain? And if so, how much? And so our predictors, or what we're using, what information it's using, is variables from the global climate model. And we're trying to predict really high resolution rainfall. And so, that's kind of an overview of how the AI works. It basically learns how to, it learns information and patterns from these weather variables like winds, and it learns how to decide how much rainfall will occur basically over a region.
So again, are you training that based on historical models, that it's looking at those historical patterns to kind of predict the future patterns?
It's because we have simulations, we have the luxury. So Peter runs these dynamical downscale simulations from these models. We have the luxury of having high resolution historical simulations, but also simulations into the future. So our AI has the luxury of having nearly 2,000 years of training data that we can train it on. So
wow.
There's no shortage of data, but there is typically we also have observations that we can also train on. So we're not just limited to training on simulations. So, but in our case, what we're trying to do is we're trying to mimic what a physics-based model is doing. So our goal is purely to be faster, because AI has AI is, in our case, AI is really we're using the speed of AI.
That was my next question. What is the difference between AI and physics-based computing? And I guess I've seen your demonstration. It looks like it's really just the speed, incredible large amounts of speed compared to physics-based computing.
Yeah. Do you want to?
Yeah. So the physics-based models are solving equations of motion, in these individual grid cells, and then we have these outputs, right? So we have the global models, and you're trying to. And then we do the dynamical downscaling, and you have high resolution model output. And as Neelesh was discussing before, the AI model's task is to look at those inputs and outputs and can it learn that process, right? Without physics, but through patterns, right? And so if it can do that well enough, it's extremely fast. And so we've spent almost 3 years, back testing and looking at all the ways AI fails, and then building robust models that can capture this. And one, little piece of tidbit of ways things fail that we've published recently is, if you train your simulations just looking on the historical data only, so those historical simulations with AI models, and then you ask it, tell us how rainfall will change in 30 years, it can't do that because it's only seeing data from the past. If instead we train our AI models looking at future simulations and historical simulations, and then ask it to predict future somewhere else or from the output of a different global model, then it can start to capture these things. So just an example of how things can fall over and
how much faster is AI roughly?
It's tricky to put a precise number because you have to keep in mind that we only predict a handful of variables. So dynamical models can predict thousands, if not tens of thousands of different variables. But the reality is that most things that most people require only a handful of outputs. So we only predict about 5 outputs, and based on those 5, it can be anywhere between 1,000 and 100,000 times faster. We don't want to put a precise number on that because there are some things that we need to. We're still not quite there in terms of operationalizing it. So, but the speed is just, it could be anywhere between 1,000 and 100,000 times. I don't know if you want to add.
100,000 is a lot. That's pretty fast.
And this actually matters because computer scientists often talk about, we sped up this piece of code by 100,000 times. Great. Okay. How long did the piece of code take to run? 10 seconds. Well, it doesn't actually matter that you sped it up 100,000 times because you saved 9.999 seconds or something. But in the case of physics-based dynamical downscaling, which I do, for the latest projections we did over New Zealand, these took 1 year to run on and used 70% of our supercomputer. So they're solving these equations for 1 year constantly.
That's amazing.
Massive of our computational resources. So this is why at NIWA we have invested in AI-based downscaling. And this is why there's computational speedups actually do matter.
And we use graphics cards, or GPUs basically, as opposed to CPUs. And with GPUs, you often might require just one GPU to run this entire AI system. Whereas with physics-based approaches, dynamical downscaling, as Peter was saying, we have to have a whole machine running. And you could actually run this on your own laptop.
Wow.
So that's the advantage. We're really lowering that entry to barrier to use AI. This is obviously, for a country like, for New Zealand, it's obviously great, but we think about the developing world. This really has the opportunity to lower that entry to barrier. We might just need to send a few, they might not need to have that same investment of resources that, they don't need to have their own supercomputing facility. We can just get them to potentially run these on laptops or smaller scale systems.
But I have to ask the question because I know someone is going to ask this question. How much electricity does AI use, and how is NIWA working to address that?
I would say that we're not like NVIDIA. We don't have the same number of GPUs. In fact, we have a handful. So the reality is we're not really draining that much power by training on. We've only got a handful of graphics cards. So I wouldn't see us in the same boat as these other organizations that are for our AI work. So the reality is that our power usage is much lower than say these big giants. I don't know if you want to add anything to that.
Yeah. So some of the big AI labs, have on the scale of hundreds of thousands.
I think Facebook has something about 660,000 GPUs, whereas we have something of the order of 8.
And so the trained models that they're developing are to, give you preferences of what cat video to watch. Do you like this cat video over this? And that requires a lot of compute because it's scaled across, Facebook's 1 billion users, right? So, you could see it that you're in fact saving computation. You're saving electricity because AI uses much less resources than these big physics-based models.
We're really targeting what we train. So as Peter was saying, there's all these cat videos. We're really only targeting several applications of AI. We're being really strategic on where we put our resources. And as we've outlined, at least 1,000 times saving of compute is the key benefit here. So if anything, we're using less resources, far less than what we would otherwise. So I would like to think we're not in the same boat as what a lot of the other AI leaders are in.
Yeah, I think that's a big relief that we can continue to do modeling on climate change using AI, especially if it's more powerful and we're not worried about the power draw. That's good. Could you talk a little bit about the shared socioeconomic pathway? I understand that the IPCC has several pathways, and you've selected one of them as the most likely scenario. How did you reach that decision? Obviously, it's requiring projection into the future, but when you want to make those predictions, you have to pick at least one of those paths. So what's the thought process behind that, and why did you pick the one that you did?
Yeah, so the climate modeling we do at NIWA, we actually model a number of these SSPs, shared socioeconomic pathways. So we've picked 3 to model. So one is a low SSP 126, one is a middle of the road one, SSP 245, and for a sort of upper range one was SSP 370. So the purpose of doing this is that in the future we don't understand well how, as we've seen recently, technological developments are impossible to predict, right? Population growth perhaps a bit easier, but how advanced technology will develop and how that will impact, renewable energy and economies going forward is probably beyond the realm of prediction. So we don't try and do that in climate science. Instead, what we say is, well, here's a range of plausible future scenarios that could happen, and these are what encompass the SSPs. So the IPCC doesn't put a likelihood on any of these. They say, each of these could possibly happen. For better or for worse, that's what the IPCC does, because then it requires users to choose one. But I think it's, so choosing, one of the upper ones is probably sensible if you're looking at a risk-based, low probability, high impact future events. But also, lower SSPs can be useful for, if there's a strong mitigation pathway in the future, what are the benefits of differences. And in the past, the very, very high SSPs and RCPs like SSP 585, RCP 8.5, have been criticized, especially when they've been referred to as business as usual, which, in the literature, a lot of people that isn't realistic, that we would, have a very high emissions future just based on business as usual. So I think, the climate science community has responded to that, and we tend to not, they aren't business as usual scenarios, but so in this particular study, the atmospheric river study, we did present results for SSP 370, which is, not an extremely high scenario, but in the upper bounds of those.
Yeah, I did look at that up, the SSP 3-7.0, and that's calling for a 3-degree warmer world, which is pretty terrifying to start with, even if that's not even the high end of the predictions, the worst case scenarios. And also that particular one looks a lot like it's been torn from today's headlines. So I feel like that was a pretty good one to pick. It's a little bit scarily accurate about depicting what the world looks like today, especially now today as in 2025, which is a bit different than 2024 might have been.
Well, and that's the thing, right? And that's a question I often get asked is, well, what pathway are we on? And I don't think it's the right question because, as you just pointed out, in a few years, things change so rapidly, and a lot these scenarios actually tend not to diverge significantly till about 2040, 2050, when the SSP 585, the emissions really ramp up. And the other ones, like SSP 370, which we modelled in this study, are sort of more linear. And then the two lower ones really, go down. So,
which is not to say we have till 2040 to figure out which pathway we want, right?
Certainly not. But yeah.
So, and I read one of your more recent papers on the results of these climate models for New Zealand. And if I'm reading it right, it said that we're expecting more extreme atmospheric rivers and 20% more annual rainfall totals in some places by the end of the century. Specifically, I mentioned the west coast of the South Island. Tell us about how you approached that, how you reached those numbers, and where the range was of other numbers you could have come up with.
Yeah. So atmospheric rivers are one of the key research areas of our team here. And so for New Zealand, what these are essentially corridors of moisture transport that come out of the subtropics and tropics and pull that moisture towards New Zealand. And when that water, these big volumes of water vapor, when they hit mountain barriers or the likes, all that water has to go somewhere and often rains out. And particularly large atmospheric rivers in New Zealand has caused really large historical damages. And in sort of the last 3 or 4 years, we've had a number of events that have sort of, stacked up around the country. And so that sort of motivated our work to look at, what's the changing nature of these events in the future. The first task was to look at our climate model output and say, do these events even happen in our climate models? Can we trust them? So we did a lot of work, looking at historical atmospheric river events and sort of the distributions of how big they are and satellite data and in the real world, and comparing those into our model simulations.
Do you take the model and run it backward to see if it matches existing historical events, and then you feel comfortable that it can run forward and also predict?
Exactly. Yeah, exactly right. So we do, to get technical for a little second, is we do a reanalysis driven run. So this is basically driving your model with, observed satellite data, observed sea surface temperatures. So it's saying if it gets those observed conditions right in the background, can it then simulate the right conditions, the right rainfall amounts, the right water vapor transport pathways that occurred for that event. And so we do a lot of back testing, essentially, a lot more back testing than we do anything else. Probably 90 to 90% of our time.
Really? Wow.
Simulations and testing the assumptions, right? Because climate modeling is as much of an art as a science. So if we make these 10 assumptions, how does that change your result?
Go ahead.
So one of the main findings from that study was exactly that in the future, with a warmer atmosphere holds more water vapor, and that tends to be more fuel for these storms. But on top of that, for particular regions, you can see changes in the jet stream, which can amplify this background warming, and particularly in the west coast of the South Island is one region where our model simulations are indicating this could become more of an issue in the future.
Does that mean the possibility of more cyclones as well?
We actually have another study which we're about to publish soon, exactly looking on this. So changes in ex-tropical cyclones, so tropical cyclones that come down and then affect New Zealand. But typically we treat these as distinct events, atmospheric rivers and tropical cyclones. They can you can get atmospheric rivers that occur with ex-tropical cyclones, but you can get independent ones. So we sort of treat them just for process-based understanding as sort of separate events.
Specifically for infrastructure, we're looking at the assets having 50 to 100-year lifespans. What kind of impacts does it look like climate change is promising that's going to impact that kind of infrastructure asset?
One thing that might be a bit counterintuitive is in climate projections, it's actually easier. We have a better sense of the changes mid-century and end of century, so 50 to 100 years ahead, than we do over the next 10 years, because that's what we call decadal prediction. They're short-term, sort of 5 to 10 years. And that has a lot, just in the climate system, there's a lot more chaos. It's hard to know next year will we have El Nino, next year will we have La Nina, and over the next 5 years will we have, more or less of these. But in the long term, where it's forced, these changes are more forced by our emissions in the climate system. That's where these changes, we can see the signal of them more. So yes, we can make projections, and we call them projections because they're conditional on the SSPs, on how much we emit. So
yeah, that's why I asked, because infrastructure projects are required under our rating system to take a look at the 100-year forecast predictions on the model and say, in general, how that's going to affect their asset. So the 100-year prediction is perfectly valid for an infrastructure asset.
Yeah, yeah. So just going on. So back to your question. So I think, and obviously depends on the type of infrastructure you're working on. And we have a project now that we're hoping to spin up soon on sort of interconnected risk as well. So like if risk across regions, but also if, after a big cyclone or a big devastating event, how does an outage here affect an outage here, and modeling those, which involves more than just climate science, right?
Cascading failures, basically.
Failures and things like this. But yeah, certainly through extreme rainfall, I think that the changes in extreme rainfall, which with climate change are quite robustly projected across our models. Our biggest rainmaker events, as we talked about earlier with atmospheric rivers, are going to robustly increase in the amount of rain they dump. And so what might have been, a 30-year, a 1 in, 30-year event, could be becoming a 1 in 10-year event, 1 in 5-year event. And that's, I think going to be the challenge for infrastructure design going forward, to be in a non-stationary climate, right? What is that?
So AI has been developing every year. It seems like we have a breakthrough moment every year on AI. Where do you see this developing over the next 5 to 10 years, and how is that going to help you in your research?
I sort of see a synergy between AI and physics-based approaches. I have a really strong belief that we need to have co-development. A lot of people think that AI is going to take over, at least in our research area, physics-based approaches. The reality is we need both. And we need to make sure we have a plan or strategy so that both grow at the same time. So, for example, we need physics-based approaches to generate the training data so we can have AI approaches. So let's say we invested all our resources into just AI but forgot about physics. Then one day we'd realize, well, our training data is not good anymore. And so AI would suffer. So I really think there's a synergy between the two approaches in terms of how they grow. So I see generative AI really, really taking off. Specifically in climate, we're seeing a lot of me and Peter's research, we're really seeing the benefits of generative AI. You might have seen a lot of these, being able to generate really realistic images of cats and dogs and people. In the same way, we can use that same type of technology to now start making really realistic and physically reasonable projections of rainfall. And that's exactly what our research has been about. So I really see generative AI being really, really phenomenal in this space, but I really hope that we continue to invest in both areas.
It's just to add to that, I think it's really exciting to work in a field that is rapid, just blowing up essentially.
Yeah, and another thing I want to talk a bit about is just briefly is uncertainty. So we talked a bit about how, if you're planning for infrastructure and the the long term. One aspect where AI is important is obviously we talked about how at speed we can do things a lot faster. And I think the reality is one reason why we need both is we can trust physics, right? We can trust physics-based approaches. And if AI can replicate those, those and learn those physical processes too, then we have a trustworthy system for generating climate projections, and we can verify. That's why Peter's talking about hallucinations, because it helps us determine whether we can trust these systems. And if we can use AI now and we trust it, we can generate what we call a large ensemble of climate projections. So basically we can understand the uncertainty in our climate risks. So currently with physics-based approaches, they're expensive. And as a result, Peter said that we only select some climate models that that are accurate, and we downscale those, we increase the resolution of those. But with AI, we can have a larger number. And that can tell us what is the uncertainty in those range of futures. For example, is Auckland's rainfall going to increase by, as opposed to saying it's going to increase by, say, 10% or decrease by 10%, we can say there's a range of possible outcomes between 5 and 30%. So we can provide more of a confident estimate of what we think that uncertainty is. And that might help a lot in terms of decision making. So I really think AI has this huge potential to help us understand uncertainty, something we don't know much about right now.
Just to add to that, the tail risks, so the real like 1 in 100, 1 in 1,000 year events is another way where AI can help, because by generating many more simulations, you can start to sample that tail risk properly.
Do you ever go back and compare it to the physics-based and make sure that it's on track? Say, pick a random point in the future and double check?
It's basically entirely what we spend all our time. So yeah.
Training is only like a small part of it, because I think we've talked about this, we really want to trust the AI, right? We really want to trust its decision making. And until we can, that's when we'll start using it. So basically, our whole research is about, can we put AI through the most horrendous tests possible so that we actually want it to fail so we can find out how to improve it more.
One of the tests we do is we produce a prediction on a day with our AI model, a prediction on a day with our physics-based model, and we take it down the hall to our meteorologists here and say, can you tell which is which? And yeah, we're doing a pretty good job when we've started fooling meteorologists.
Yeah. So it's getting good. But I think the earlier versions of AI, we weren't able to fool it. So it's basically, we're getting better over the last couple of years.
That's fantastic. That's good to hear. And I'm glad it's being put to good use rather than just cat videos.
Yeah.
So what's the one thing you think that our listeners who aren't in this field can actually do to help you promoting the understanding and use of climate models?
I think, I think the fact that people are interested in the output from climate models, I think this has sort of been an explosion in recent years of, certainly for us anyway, we talk to a lot of consultancies now and in the insurance companies, interest in the data. And so we've been working with them to understand how to use the data appropriately. What are the limitations of the data, such and such. And these will change depending on the application, right? So it's hard to give general.
It's about understanding their context. One question that we really want to understand is, how do you see uncertainty being useful for your decision making?
Well, great, Peter. Neelesh, thank you so much for being on the show. I really appreciate it.
Thanks so much. It's been fun.
Thank you for joining us at Infrastructure Connections. Please take a moment to follow us wherever you get your podcasts, and we want your feedback. Drop us a line to let us know what you think. Stay tuned for the next episode, where we talk to Sam Donaldson about the Task Force on Nature-Related Financial Disclosure. That's coming up next on Infrastructure Connections.